Hello everybody, I'm Carla and I'm going to start to present our paper about exploratory analysis of public transportation data of Curitiba, Brazil. And we divided our presentation in 4 topics, as you can see here on the side. 1. Urban mobility and IoT, everything connected everywhere. 2. IoT as an enabler for better urban mobility solutions, the Curitiba case of study. 3. Methodology and results, data available and what we can do with it. And 4. Conclusions, our work contribution. Urban mobility and IoT, everything connected everywhere. After a lot of research, we highlighted 4 important points to make urban mobility and IoT works in order to have everything connected everywhere. Sustainability, access, comfort, and efficiency. Sustainability. By improving the understanding of the user perception of the quality of available public transportation modals can positively impact on the city's sustainability. Access. Public policies should prioritize public over private transportation. Comfort. Urban mobility policies aim to presenting the guidelines for planners to develop projects in an appropriate way, prioritizing the well-being of users. And efficiency. On-demand information gathered by IoT devices can be made available to passengers and operators for better planning of trips ahead of time or quickly and efficiently reacting under non-predicted events. Talking about urban mobility and IoT in Curitiba, we have 3 elements and I will describe here: Curitiba, URBS, and PTS. Curitiba is the capital of Paraná State and is located in the southern region of Brazil. City that followed a master plan since 1960s and has the urban mobility and the integrated transport plan. URBS is the company that manages public bus transports in Curitiba. Public transportation system integration that connects Curitiba and the metropolitan area. Other elements that we use here at this paper are time of arrival and departure of each bus, comprehensive list of bus stops, information on bus routes, and all these 3 elements lead us to a quality of provided transportation service. IoT as an enabler for better urban mobility solutions, the Curitiba case of study. About urban mobility solutions in Curitiba. In Curitiba, you can have a wide availability of new applications. Rent a bike or a scooter or even asking for a car, which are easily accessible from smartphone apps. Applications use great amount of data, geolocation information, and collect data about the user profile, mainly for advertisement purposes. Application improvements. Collected information can provide ways to improve available services. On the other hand, the inefficiency and the low quality of service of Curitiba's PTS have been pointed out as the main reasons for people to change from public to individual or shared transportation solutions. And unfortunately, there is a lack of integration of the PTS with the other modals that could help the user to overcome the last mile. How the information provided by the URBS IoT devices on buses could be helpful to improve the user satisfaction to keep or attract users to the PTS. About the PTS information system of Curitiba. URBS and IPUC are companies and they provide open data about the city and the PTS operation. Buses. PTS of Curitiba has 251 bus lines with 1,229 buses running on a daily basis. Onboard and GPS. Bus data includes information about the bus speed, schedule adherence, estimate trip time. About IoT devices. All data collected by the bus is also stored on a local media and updated to the WoCCES database, DB, later. NC3SL. A copy of the daily collected data of all buses is uploaded from the WoCCES DB and kept at the C3SL repository as open data for research purposes. Information delivered both real-time 10 seconds and near-time 60 seconds.
Hi, my name is Bruno. I'm going to present you throughout the methodology and conclusion of our work. In this section, I'm going to talk about the methodology used in our paper. As you can see in the slide, the data was collected from the IoT system and deployed to the PTS operation control. Then it feeds a system developed to extract useful information for the PTS users about the scheduled adherence of buses from a specific bus line. The system validation was done by comparing peak hours reports from URBS. In our work, scheduled adherence is associated to the bus departure and arrival time set at the official URBS timetables. These timetables are set for all bus lines associated to the time intervals shown in peak hours timetables, also in the slide. The bus line schedule differs for workdays, weekends, and special events. URBS usually checks the scheduled adherence only at a few bus stops, the initial, the intermediary, and the final bus stops of a bus line route. Some parameters were defined to perform our analysis, as total delay time, amount of delays, total of early arrival time, amount of early arrivals, number of scheduled bus occurrences within the allowed time interval, total of analyzed days, and total of days with some occurrence. To bring meaning to that information, we define that integrity percentage as the rate of total of days with some occurrence and total of analyzed days, delay average as the average value of total delay time, early arrival average as the average value of early arrival time, user perception as the difference of the delay and early arrival average. Taking that in account, the analysis of IoT data from the PTS of Curitiba should be able to characterize the peak time behavior of the system in terms of forecast schedule adherence. Due to the number of lines and the amount of data to be handled, we limited our analysis to 3 bus lines that were chosen according to the main characteristic of bus lines in Curitiba: express, feeder, and direct bus lines. The figure beside shows the itinerary of bus lines 303, 507, and 924. Hereby, bus stops refers to a place set for board and disembark of users of PTF buses. Bus occurrence refers to the physical presence of the bus nearby the bus stop. In this slide, we can see some methods and technologies that helped us to handle data. URBS data from February to April of 2019 were collected from C3SL site for our analysis. The data was compiled to a JSON file. Similarly, other files were generated for each bus line, comprised the geolocation of each bus stop, and the scheduled time arrival on each of them. URBS metadata with JSON is a standard for PTS serial data, and the files can be up to 500 megabytes, corresponding to up to 5 million records. Some files have their structures adapted, allowing to be correctly read using Python. Details on these adaptations can be found at the project repository on GitHub. In order to classify bus occurrences inside a certain radius, a time interval of 60 seconds was set for each sample time as a reference, reported inside the circle around the bus stop under investigation. Once a geolocation inside the circle is detected, all samples collected 60 seconds before and after this moment are considered. Exemplified, a bus can be at most 50 meters of distance from the bus stop in some moment that cannot be more than 2 minutes apart from the sampling time. If a bus occurrence is detected inside this interval, the occurrence is classified as OK. Bus occurrences greater than 350 seconds, 11.5 minutes, are set as delayed or early arrival depending on the official scheduled time. It represents these conventions considering the frequency reported table peak hours we saw before. Now we are going to look at the results the use of that methodology brought to us. This table shows a selected range of data arranged by expected time. This is a simple example of how data is organized before being processed by our algorithm. Now we can see a chart with the variation of delays in blue and ahead times in red for line 924 Terminal Santa Cândida. And here we see the user perception for the same line. We computed contiguous and/or periodic incidence of delay or ahead average greater than 3.5 minutes and selected them for a closer analysis. The figure in this slide shows them in blue for several lines compared with those provided by URBS in green. These results emphasize that not all bus lines have the same behavior regarding the peak hours. They show us that bus frequency could be better distributed. From this figure, one can notice that most of the time the peak times of the bus lines are not necessarily synchronized for all the investigated bus terminals. Subjects applied to public transportation solutions. A case study based on available open data of Curitiba was carried out for IoT data gathered from its bus-based PTS. Our study revealed challenges of processing big data and provided insights on the PTS operation. Our work contribution towards approach to understand the user perspective on the PTS quality of service and possible applications using qualitative and quantitative analysis. As a proof of concept, our analysis found out important information for users, operators, managers, and planners of the public transport network in Curitiba. The development of a real-time passenger information system that integrates transporting information with collective vehicles location is a potential future work based on our methodology, which might be delivered via mobile apps to the end users. Such implementation leads to improved information available to help users and bus companies by reducing the waiting times at the pickup points and delivering more efficient services. Future work includes the integration of a methodology for mapping the direction of the bus and consequently the line bound. A further integration between the customer service center and PTS could be carried out to identify potential targets for improvement.
And our team layout, who is part of this team? That includes me, Bruno, Professor Daniel Pigato, and Professor Keiko Fonseca. Thank you for your attention and thanks everybody for this opportunity.